Well, good morning or good afternoon, depending on where you happen to be in this country. I guess it's morning everywhere in the United States, so it's still morning, still in the morning. Welcome to our June edition of the ABA Broadcast Engineering webinar. This is a webinar that we put on every month, the third Tuesday of the month, and we have various speakers and technical and legal information that we share with everybody, and hope everybody gets some great information about it. Want to thank our sponsor, Max Connect Group. They have been sponsoring this webinar for a number of years, and also they uh, sponsor our radio and television broadcast engineering classes that we do in Birmingham. We have a radio class coming up, as a matter of fact, next week, and a television class coming up in August. We've been doing those for 10 or 12 years now and had some really good attendance. We have people coming from all over the United States, from Alaska and California, and Jeff, we even had some come in from Canada at one time. So the Max Connect Group has been our underwriter of all the activities that we do here with the ABA. Uh, we want to bring in right now a stranger, our co-host, who has been on the road from time to time. But John, welcome back to the webinar.
Well, good morning, and it's good to be back, even though I'm only going to be here for a few minutes. I'm actually out doing some field work today at a tower site, trying to do some repairs on some tower lights. So we all know how important that is and how we're working. But anyway, it's good to be a part of the group again.
Okay, and you had something you wanted to share about EAS before we actually got started, I think.
Yeah, before we get started, I always give the EAS updates, and of course, we're several months past the required deadline for upgrading your Sage units. And Larry and I were talking earlier, and there seems to be a fairly large number of people who have not done the latest updates on their Sage boxes, and a number of people that have not updated their DASDAC boxes, which means if you're checking your logs each week, the station log is required, and you're not getting your weekly IPAWS test from Washington that comes in at 11 o'clock roughly Eastern time, Central time, and Mountain time, and Pacific time, then your software is outdated. And so you definitely need to get that software update taken care of as quick as possible.
Yeah, I see that on our database that we're monitoring stations here in Alabama, and people that don't get the IPAWS test, I look over on the side, and it still says if they have a Sage, it shows version 95. So that's a real problem. So that's a good point to bring up there. Our
Yes,
yeah, go ahead.
I said yes, definitely.
Yeah, okay. One of the things that I wanted to share with you today, the if you watch the weather forecast very much, the meteorologists are all excited about coming up Thursday. Summer is starting, but if you have walked outside in the last few days, I think it's already here at just about everywhere in the United States. And unfortunately, when summer gets here, it creates a lot of problems for engineers, both in heat and also with lightning damage. This is a big, especially down in the south. We have just about every week we'll have a thunderstorm with lightning and surges, gets into everything. So I thought I'd call our lightning expert. Oh, Jeff Weldon. Everybody seems to know him, and we called him and said, Jeff, come to talk to us and tell us, how do we get rid of all that lightning damage? So, Jeff, welcome to the show, and we look forward to hearing what you have to say today.
Well, thanks, Larry, and it's good to be back. It's been a few weeks, but the funny thing is, I'm in Wisconsin at the moment, and coming in last night, coming up 41 to Oshkosh was it was a spectacular lightning storm going on there. And this year seems to be a bad one for that. I don't care whether you call it climate change or weather or what. There's some years where the lightning is going to be a whole lot worse than others. And that's kind of one of the things we're talking about here, it's I got a few topics. Lightning protection is one of the big ones that I'm going to hit, but I'm also going to talk a little bit about the air handling and cooling the site. I'll throw the housekeeping comment in that we do. I want to make this as interactive as I can, so I've got the chat window open. So if you throw anything up or anything comes to mind, just throw it in there whenever, and I'll fit it right in as I go. I don't see any reason to hold on formalities here at all. So, like I say, the more we get involved, the better off we are. And I see that I've got the subtitles turned on my PowerPoint, so I'll just leave those going too. It might be useful for the recording if I start stuttering in Canadian or something. And that is something else to think about. Larry was saying that it was morning everywhere, but I'm pretty sure that Puerto Rico is on the Atlantic time zone, so it was just barely noon there. But anyway, one of the things we run into a lot when we do site inspections, and I know John knows this, Larry knows this, and anybody who's walked a transmitter site at all knows this, is that you need to give it a once over here and there. You need to take a look. There's an example here, and I don't know the backstory, but the tower on the right, every single ground connection, every ground kit on the coax all the way up the tower, and it was a 700 or 800-foot tower out west, every single ground kit had been disconnected for one reason or another. And I don't know whether it was when they painted the tower or what, but all the ground kits were just hanging there loose. Now, that's an issue for two reasons. Number one, if you've got two conductors running parallel to each other, like a big steel tower and a big copper coax, and you run a lot of current through one of those, you've got a capacitor, so you can induce a lot of current in the other one. Number two, is that a 24-inch ground lead or a 36-inch, those are the two common sizes, makes a really good antenna for re-radiating a lot of spurious stuff. So I've run into a lot of LTE interference complaints, for example, that have been traced back to grounding kits that weren't bonded well on the tower. And that's something else to realize. We're going to use two words here a fair bit. I'm going to talk about grounding and I'm going to talk about bonding. Effectively, grounding is where you attach the wire and bonding is how you attach it. So bonding could be a mechanical bond, like just screwing two pieces of strap together. Could be an exothermic bond, like CAD weld, silphos, silver solder, brazing, whatever have you. That'll be my preference whenever I get it, and we'll get into a little bit about why that's important as we go too. As you can see, this is a presentation that I built most recently for the SBE's NSRF 101 workshop, the 2-day workshop prior to NAB this year. And other little shout out while I'm thinking about it, and I know my camera's kind of hidden, but Larry was talking about Max Connect sponsoring, and I am quite literally running this session from a hotel in Oshkosh. Hotel internet's not the best at the moment, and I'm running it on a Max Connect unit. So just a little shout out for them. But on the other hand, if I drop out, we'll know who to holler at. So keep that in the back of your mind too. All right, so I got called to a site in the eastern part of the US one day. Well, called to a site. I'm in sales now, not tech support, but I still wander into a site now and again. And they were having quite a few failures. They were having a lot of failures, like almost half the price of a transmitter worth of failures on a transmitter that typically doesn't see that many failures. So one of the things we noticed when I got out there was that what you're looking at in that right-hand picture is the grounding for the facility. That's the electrical ground coming out. And you can see it's just a couple of soft ground copper, basically AM ground radial wire that's been twisted together. Once that oxidizes a bit, that's not a really good ground. And the thing to remember most about grounding is that wherever possible, you want short, straight runs. And you also want to have what we call common point ground or a star ground, single point grounding. Now, that can get a little tricky. Like if you're in a Cellco building or cell company type building, the kind that have the green wire around the ceiling, the halo ground, those work great, but they've typically got a ground lead coming down from that halo at all four corners of the building and going outside. And if you connect all of those to a ground rod, you would better strap all those ground rods together. Otherwise, you've just totally lost control of your grounding. You got circulating currents everywhere. I tell people I like halo grounding done right. The problem is I almost never see it done right. So that's something to pay a lot of attention to. One of the other things I see a lot of is there will be an AC ground coming in from the power pole outside, and it'll come into the building at one side, and then the coax and the and tower ground are at the back side on the opposite end of the building. And if those aren't bonded together, that's a problem. And in some areas, you'll get some older electrical inspectors that'll still resist that. Well, since around about 2005 or 10, I don't remember when, but Article 250.4 of the NEC, the National Electric Code, is what deals with facility grounding. And in the early 2000s, that code was edited to specify that facility ground and the AC ground, entrance ground, must be tied together. The challenge is some states follow different versions of the NEC. Some states don't follow the NEC at all and rely on state electrical codes. So you absolutely want to speak to an electrician who's current on that to make sure that that may or may not, that won't be an issue, because not having them tied together is going to be a problem. So that's one of the big things is, like I say, short, straight grounds. And this slide deck will jump around a little bit as I go from one thought to the next, but we'll see sort of a theme evolve as we get through it. And the grounding is arguably one of the most critical things. Now, grounding on its own isn't going to solve all the problems. You need to keep the place clean, and that is also something that I run into a lot, where the air filtering may be less than stellar, I guess. And so, you know, that's also a challenge that we want to look after. Back to the grounding and the tower ground, and say this PowerPoint, it got put together, and I don't know what happened Microsoft World when I saved it. It doubled some slides and threw some around in different orders. And anyway, the getting back to the tower ground, you got your ground kits on the tower. Those are fairly, relatively speaking, low gauge, small gauge wires. You know, they're typically in the range of a 6 gauge, give or take, 6 to 4, in that range. And relative to, say, a 4-inch strap, that's got a fairly high resistance per foot and a fair degree of inductance for any high frequency component. So it's not an ideal ground. The real purpose of those is to help bleed off any surge as it starts to build up. And they definitely need to be installed. They need to be there. They also break up that capacitance that I was talking about earlier to cut down again on inducing stuff. But you really, once you get to the base of the tower, that coax needs to have a ground kit installed. I prefer to see them where the coax comes into the building, because you'll typically have a couple of coaxes, maybe an STL coax, transmitters, maybe a translator or two, and you can put a bulkhead panel right at the entrance to the building and put a ground kit on each of those cables and connect it to that bulkhead, and then a single strap running down to your reference ground point. You know, short, sweet, and simple. And that's really what we want to accomplish. Get back to there we go. Yeah, see, like I said, it jumps around there. So we definitely want them short and straight where we can. We want everything common together. What we don't want, and I've run into this in 1 or 2 sites, is we don't want, as I said with the halo, a whole lot of ground circulating current. We want each piece of equipment connected to a reference point, but we don't want this piece of equipment connected to that piece of equipment connected to that piece of equipment, and maybe have both ends connected to ground. Like I said, ground loops are a challenge, just like they are in audio wiring, where you get the hum induced on a lot of stuff. You can run into challenges with lightning protection. Where that becomes an issue, especially if you're working with a site that has evolved over the years, then you can run into challenges where a new piece of gear gets added, a new ground wire gets put in. After a little while, somebody else comes in, maybe changes some grounds, maybe adds some new, maybe removes one. Another piece of gear gets added, more ground, and at some point in the game, you totally lose control of what goes where. So that comes back to documentation. If you don't document it, if you don't know what you've got, how do you know how to fix it? So and I tell people there are times when sometimes it's almost easier to rip it out and start over. Now, one of the things I mentioned earlier, and I talked about grounding and bonding and how I prefer exothermic connections, and CAD welding is a good example. So that picture is a CAD weld mold that I found on Amazon. You can buy CAD weld molds on Amazon now. So I mean, something that is quite literally designed to go boom and permanently connect two conductors is easy to get now. It used to be you could only get them in an electrical supply place, but yeah, Amazon, who knew? And the good thing about it is that at that point, you're not relying on compression connections. And I really don't like compression connections. A challenge with compression connections is that anytime you have a wire in a clamp, and it's just a screwed down clamp, copper's malleable. It's this very soft metal, and it will deform to displace any air in that connector. So unless you manage to get it yanked down tight enough to displace all the air on install, then in a week or two, that copper is going to have deformed a little bit to displace the air, and that connector is now loose. And I mean, how many people have run into a situation with a crimp connector, for example, where somebody didn't have the proper crimp tool and just squeezed it with a pair of dikes or beat on it with a hammer or whatever, and that's it comes loose after a while. So if you're going to do a crimp connection, it's essential to have the proper tool to do the job. If you're going to do a clamp connection, and in some cases you don't have a choice. You know, if you've got a ground wire and a flat like a bulkhead panel, it's hard to weld or solder a wire onto a piece of 4-inch by 1/4-inch copper bar. So in that case, you're going to have to use a lug of some sort. And when you do, put it on. If you can't solder the lug on, like putting a solder lug on a piece of wire or crimp lug on and just soldering it in place, if you've got to use the clamp connector, make sure you come back in a couple of weeks and give it a quick tighten with a wrench, and then come back a couple of weeks or months later and give it another tighten. And I tell people I do it in 3 stages. Come back in 2 weeks, come back in 2 months, and come back in a year. And at that point, you can probably walk away from it. You've probably displaced all the air that's going to be displaced, and it'll stay tight forever. But I've walked into a lot of sites where they had 2-gauge ground wire running around for the grounding using just those little screw down clamps. And I walked into one, and Arkansas owner was so proud of this new site. And I walked in and grabbed the main ground wire coming out of the building where it went to the clamp onto the ground rod and stood up holding the end of my hand. There's over 3 or 4 months, it had deformed enough that I was able to pull it loose by hand. So, and then I've got a picture of the owner actually brazing the same wire onto the rod. But that's the point. If you've got to use a screw connection, make sure you allocate the time and set the reminders to come back and retighten them on occasion.
Hey,
And
Jeff,
then,
let me
yeah,
interject something real quick, Clyde, and get your comment on it.
yeah.
A number of years ago, I had a big tower, 1,200-foot tower with FM antenna on it. We decided to put lightning dissipators up on the top because they
Mhm.
seem to work really well. But I was instructed by the company, do not tie those things to the tower steel. You got to have a separate drain wire coming down. And his comment, and it sort of made sense to me, his comment was tower steel, while it's a good mechanical connection, every 20 foot or so you got a flange, that's not a
Mhm.
really good electrical connection. That's
Correct.
why it's needed to put a drain wire. The only thing I had handy was like you say, it's a number 6, and we had taken down from an old lighting system on the tower, and we ran
Mhm.
2 runs of that number 6 up there and tied it to the dissipation array But in about a year or so, we had to go back and put a 2 aught up there because there was so much current going up that drain wire. It was melting the insulation and was running down the leg of the tower.
Yeah.
So
So
you might comment on that.
so a couple things. Number one, you're absolutely right. A tower is a terrible electrical connection, especially a tall one, because you got, like you said, a joint every 20 feet or so. Number two, a piece of wire is a terrible ground because if you look at the ohms per foot, and that tells you how bad the tower is, because a 6 gauge wire or a 2 gauge wire even has got fairly high resistance per foot compared to strap. And this is why, like I always say, given a choice between strap and wire, I'll pick the strap every day. A 4-inch strap, for example, has got a resistance of about 0.0016 ohms per foot, whereas a 2 gauge wire is about 100 times that. Now you're still less than an ohm per foot, but it's noticeable. Other thing is if it's a dissipation array. Now, see, there's two things I see on towers. There's lightning rods, which you need to run the current to ground, and then there's the pointy dissipation arrays like static cats. And those are corona discharge units. They don't technically really need to be grounded at all because all they're doing is just dissipating the energy between the points. But I mean, it doesn't hurt to ground them. It's just I'm not sure if it would be that much benefit. Now, having said that, I'm not going to argue with the guys that designed the stuff either.
Well, the way that I understood how those things was, and he came and did an SBE meeting, and he talked about lightning and says compared to a capacitor. If you got a capacitor with two plates and a dielectric, and the voltage between the two plates get high enough, it'll arc over and blow up the capacitor. If you look at the cloud as one plate and the ground is another plate and the air is a dielectric, you've got a capacitor. There's not much you can do about the charge on the cloud and not a whole lot you can do about the dielectric, the air. But if you can remove some of the charge off the bottom plate, being the ground, then the difference in potential between the two plates, the ground and the cloud, never gets high enough to arc over and generate a lightning strike. So the theory, as I understand it, and I may be off in left field, but the theory that I understood was when the wind's blowing during a thunderstorm, it will discharge the charge that's on the ground off those points on the dissipation array. That was the way I understood that they work, because he said if you're mind to go out there with a pair of binoculars during a thunderstorm, you can look up at the array and the tips will be glowing blue.
Yeah,
Now, I never did that, but I know that we did have to replace several of the bars over the years because they were blunted down to about half size.
yeah, and the way those actually work is it's intentional corona, and I mean, so any sharp point in an electric field, you know, sort of like a Van de Graaff generator, where if you stand there and you can touch it or create an arc on purpose with a sharp point. And so again, I'm not sure. I guess you would need a ground reference. So the wire bringing the ground reference up there would be a better than running it through the tower. Otherwise, you know, you're just floating the thing in midair. So I see the value to it in that regard. But the big thing draining the current is basically the arcing between the points. And yeah, they're sacrificial. They're meant to disintegrate rather than blown. They disintegrate so your equipment doesn't, I guess is the best way to put it.
Sure.
And yeah, I'm a fan of those. I've heard a lot of people poo-poo them, but I can tell you, like with us on the northeast coast, we get a lot of wind-driven snow, and a windy snow will typically be really dry, so it builds up a lot of static. And a good point discharge system will be the difference between several hours off air because of SWR shutbacks versus just ticking once or twice every couple of minutes while it's snowing. So yeah, they make a difference in that regard. Or like you said, when the storm's approaching or going away. I mean, once the storm's overhead, if lightning's going to hit the tower, it's going to hit the tower. There's not a lot you can do, but you're right, you can minimize that capacitance. Cortana used to have a really good paper about that, and I'm not sure who's doing their stuff now or if they're still around, but that'd be worth hunting that down. If you search Cortana and dissipator arrays. They had some really good information on that quite a few years back. Now, I mentioned the single point grounding, and this is huge. And in a lot of cases, like in the little sketch I've got here, you can do it as a tree. And this is an example I gave somebody to go because they were asking, well, would this work at a studio? And it's like, sure. Each room, studio, production room, whatever, has its own ground point. Maybe the TOC has a ground point, and then you tie all the grounds together to your facility ground, and so you've still got single point grounding. You just do it in a little more of a branch format. Again, the goal is to try to avoid running from one thing to another thing to another thing and then back, and just creating ground loops. Those can be a little hazardous. So we definitely don't want to see that. I ran into a site in San Antonio a bunch of years ago where they'd put in a transmitter, and he called me up and he goes, "Hey, I installed those ferrites y'all gave us." And I said, "Cool." And I'll talk about ferrites in a bit too. But he goes, "Yeah," he goes, "We got a problem. The ferrite on the main transmitter is getting warm." And I said, "Yeah, if it's getting warm, then you've got a ground loop because you need to have the feed and the return equal." And he goes, "You don't understand. The main transmitter's turned off. We're on the standby." And it turned out they had so many ground loops that there was a lot of RF current going through the shield of the main transmitter's coax, even when the transmitter was off. The cool thing is he discovered how bad the imbalance was when he turned the main transmitter on. That ferrite exploded. So it's a pretty good audio-visual troubleshooting tool some days too. But that is the kind of thing that a single point grounding will help eliminate. One of the other things that I've run into a lot, especially with co-located, as we see more and more translators going in for AMs, you co-locate an AM and an FM, and you can a lot of times get the audio from one onto the exciter for the other, depending on what you've got for gear. And the grounding will quite frequently be a contributor to that as well. So just something else to think about. That's less an issue more these days with everybody running audio over IP and AES audio, but definitely if you're in an analog world, then it's pretty easy to induce RF onto an audio cable shield. So something else to think about. I don't know how many times you're going to see those two pictures, or that one too, but more than once. So the goal of grounding, and you'll see in most of the pictures I show, there's something wrong. And this is a site fairly local to where I am now, and every cable was beautifully grounded, nice ground kits, had bulkheads installed here and there. The challenge is that the grounds are a lot longer than they need to be. Remember I said short and straight. So the ones on the left side, they're going out and looping back, and you don't need a drip loop indoors. And same token, if you're grounding your surge protector or your coax at a bulkhead, short and straight. Don't loop it unless you absolutely don't have a choice. Not because it's really all that much an issue, but again, we're playing a current divider game. So if you start at the tower and head back to the AC lines, which are basically lightning is going to, because you get a big surge of current coming down a tower, and once it hits Earth has so much resistance per foot. Say 3 ohms per foot. I mean, I'm making that number up, but it'll be right for some part of the country. But say you've got 3 ohms per foot. Well, if you run 100,000 amps of current in a lightning strike down that tower, 3 ohms per foot, if you got a 3-foot distance, that's 9 ohms. 100,000 times 9 ohms, E equals I times R. That's 900,000 volts you've developed from left foot to right foot, which is why they always tell you if you're caught in a field in a lightning storm, put your feet together. There's more to that story. You put your feet, anyway, I won't get into it in a recording. But point being that everything we can do to minimize the resistance of the path we want the lightning energy to take, that's what we're going to want to do. So if I can make those wires 6 inches shorter and they've got a resistance of 1/10 of an ohm per foot, well, collectively speaking, that may be a couple of ohms that I've taken out of that path to ground, or that path between ground and the surge protector. So that's the ultimate goal here, short and straight wherever we possibly can. If you've got strap, for example, and you have to go around a corner, and you know how you can fold it over at a 45-degree bend to make a 90, hammer it flat and then solder it at the bend so that you've actually got a bend, or do 245s instead of a 90. So you got more of a gradient and less of a sharp curve. Lightning doesn't like to turn corners. Any amount of significant current doesn't like to turn corners. So short gradual gradients whenever you can. This one is an example. It's one of our Q20s, 20 kilowatt FM we built a bunch of years ago. I know there's one or two of them, or have been one or two of them in Alabama, and I know there's a bunch of various other. This one happens to be in Missouri, and they were having quite a few power supply problems. And we came in, or I came in, and started at the tower and walked back, because that's the easiest way to follow your grounding, is to quite literally follow your grounding. So you start at the tower and you walk your way back. And what I found was there was a beautiful, nice, bright, shiny ground strap at the base of the tower, and it went into the building, came around to the ground connection on the back of the transmitter, and the surge protector had a ground wire, and it was also had a wire running over to that ground strap, what you're seeing here on the coming out of the conduit. Now, two things. Number one, as I followed this ground strap from the tower into the building, the one thing I did not see was a ground rod. So any energy coming down that 600-foot tower, or whatever height it was going straight onto that strap, right to the back of the transmitter. So that's item number one. Item number two, the primary ground, which is relatively speaking a fairly high resistance wire, that 2-gauge cable, is going through a conduit. Now, we'll talk about ferrites in a bit, but a ferrite is a ferrous material. And if you've got any high frequency component on something and it goes through a ferrous material or an inductor, then that presents an impedance. Well, steel conduit is also a ferrous material. So you've got a one-turn inductor with that wire running through that conduit, which means that you're adding, again, more resistance. So in this case, all this energy is hitting the ground connection at the back of the transmitter. There's no easy discharge path through the surge protector to the power lines. The only place for the energy to go to discharge was through all the switching supplies. So we put a ground rod out at the tower. We replaced the AC entrance ground rod because it was only a couple of feet long and driven at a pretty steep angle, and put a proper rod in there, bonded those two together outside the building, and then fixed the grounding to the surge box. And in the process of doing that, their failure rate went from a whole lot to virtually none. I won't say none. They have had one or two failures, but it's one or two failures over 10 or 15 years, not one or two failures every single lightning storm. So their repair cost has gone from thousands of dollars a year to less than $100 a year for that purpose. Okay. This was the reference ground, by the way, an easy mistake to make. There was a piece of what looked like ground rod, and that's what they bolted to. Well, it turns out that was the J-bolt to hold the building down, not a real ground. So we ended up running out to the ground rod. And I say, it's just sometimes it's the simple things that will get you. And you'll see something and you'll look and you go, that looks like a good ground point. And I had one guy, as an example, at a friend of his was an electrician and told him that in a pinch, if he didn't have a ground rod, that a cold water pipe would be a good ground. Well, the guy doing the install wasn't electrically oriented. It was a station owner, and he was just taking the best advice he could get. So he found he had a cold water pipe in the transmitter room. So he bolted onto that with a clamp for his ground connection. This electrician putty didn't tell him that PVC water pipe is not the best ground. So that's what he was connected to. But that's one of my favorite pictures too. Other thing is, and this comes back to what we were talking about earlier, Larry and I were talking about before we started, was you need to have a checklist, and part of that checklist needs to include a walkthrough, a scheduled walkthrough at every site you maintain, whether you're a contract engineer or a station engineer or a corporate engineer. You need to do a walkthrough on a periodic basis. Now, how often that is, that'll be determined by you and your site. If you're up here in Wisconsin and you don't have a problem with people collecting copper for scrap value, it might be measured in once a year type deal. If you're in a little less desirable neighborhood, like this one in Arkansas, then it might have to be a little more often. And this was one where they were losing a lot of stuff on their 50 kilowatt. Everything in the building looked perfect. Point to point grounds, bolted down nicely. Things are beautiful. Got outside and moved that bush. That's also where I discovered what chiggers were, but that's a whole different story for another day. And discovered that the ground strap didn't go anywhere. The ground system had been lifted. So, they didn't have a ground. And that's the kind of thing that, it needs a physical inspection on a regular basis. Walked into a site not too far outside of Montgomery a while back, a few years ago, and this was owned by one of the bigger site groups, and discovered that the bulkhead was there. Everything, all the coaxes were nicely connected to the bulkhead. 2 ground leads that didn't go anywhere. They were cut about 6 inches off the bulkhead panel. So again, it needs physical inspections here and there. Okay, talked a little bit about ground rods. We need ground rods. In the ideal world, they'll get to the water table. In some parts of the world, that's not possible. In which case you make do with as much copper as you can. I like chem rods if you're in a really high and dry situation, like on a mountaintop where you can't get to the water table. You can do a chemically augmented ground system that is not a bad thing. Thing to remember with ground rods is that they have basically it's called the electrode interface hemisphere, but a useful radius around the rod that's essentially equivalent to the amount of the rod that's underground. So if I've got a ground rod buried 10 feet underground, then the useful radius is ballpark about 10 feet. So I could put 2 10-foot ground rods 20 odd feet apart, 22 feet apart, and they'll be maximum efficiency, maximum effectiveness. If I put them any closer together than that, then I'm just reducing their, I'm not reducing their, I mean, they're still ground rods, they're still useful. But like 2 ground rods, if you put 2 10-foot ground rods a foot apart, you basically did all the work to drive 2 ground rods and got the equivalent of 1 11-foot ground rod. So, again, you're just minimizing the efficiency of the system. So, and I give an example. I run into a lot of situations where somebody have an 8x8 transmitter shack at the foot of a tower. They'll have a couple of ground rods at the base of the tower. Then they'll have a ground rod at each corner of the shack and at the midpoint. So, grand total of 8 ground rods around a building, where one at each corner or one on diagonally opposing corners probably would have been plenty. Or depending how close you are to the tower, you put one at the tower and one on the far corner of the building. So, again, it doesn't hurt to have a few more, but it's unless you're in a high dry area and you're trying to make it up with a lot of copper in the earth, then you hit a point of diminishing returns pretty quickly. So that's just something to pay attention to. Talked about ferrites earlier, and the most useful thing about ferrite is, well, 2 things. Number one, it adds a little bit of inductance. So for any high frequency component in a lightning strike, and lightning does have a fast rise time and typically some ringing at the carrier frequency on it. So there is a high frequency component involved. So a ferrite makes an inductor, which means that it's going to increase the effective impedance to a lightning strike. And as I said before, this is a matter of degree. We're playing a current divider game where we're trying to make the path through our equipment look the least attractive, and the path through the surge protector, which we'll talk about momentarily, to ground, the most attractive, or from the surge protector between the AC lines and ground, and we'll talk about that in an overall view shortly. But so the ferrites will help that way by raising the effective impedance of the equipment if you put one on the cables like coax and AC lines between the equipment and your common point ground. The other thing that they do is that if you get a common mode surge, so you got a feed and a return going through a ferrite, And as long as the currents are equal, the ferrite's just an inert lump of carbon and iron filings that does absolutely nothing. But if you get a surge on one or the other, say you got a tower strike on an AM that spikes the center conductor hot, or you get a tower hit on an FM where the coax shield gets hot, then in either direction, when you get a common mode surge, a surge on one conductor, not the other, the ferrite will saturate, and it effectively induces a magnetic field that tries to induce current flow in the opposing conductor. So you essentially equalize your surge, if you will, between the two conductors. And that's a vast oversimplification, but that's effectively what it does. So the goal with a ferrite is, like I said, it's not on its own going to do anything, okay? So if you've got bad grounding or don't have a surge protector, slapping a ferrite on there isn't going to do you any good. You're still going to have failures. But in this current divider game I keep talking about, if you've got the good grounds and a properly installed surge protector and a well-established path for lightning to flow, then anything you can do to, again, make the stuff we don't want to blow up look less attractive for the path for lightning energy to flow, the better off you are. So where do you put ferrites? Anywhere where you have a feed and a return. You can put them on all your coaxes, STL coaxes, satellite dish feeds, on obviously your antenna for your transmitter. Put them on the AC lines. One ferrite with all the feed and return going through it is just fine. You can wrap the individual legs through ferrite to make chokes on each one. That's, again, a little less of a benefit, but it's still a benefit. I tend to just go with one ferrite over all the leads. If you can loop them around and run them through again, so much the better. You just went from a one-turn choke to a two-turn choke. So you double the inductance or double the impedance, because that's linear math. Now, the benefit on the current divider, that's a different story, but again, little bits. It's all a matter of degree. Okay, so the surge protector is the third piece. You got the single point grounding, short straight runs. You got the ferrites, which are, like I said, probably should have been third. And the surge protector, that's your triumvirate for lightning protection. And the surge protector needs to be as close to the mains entrance as you can get it. Reason being that the electrical wiring to the surge protector from the mains panel will be the highest inductance or highest impedance conductor, because you'll have a ground strap, or all your other grounding will tend to be relatively lower inductance or lower impedance than the electrical wire. So get it as close to the mains panel as you can. It needs to have a path between ground and AC. Okay, the deal with a surge protector, and most of the common ones are MOVs. There are other ones that contain silicon avalanche diodes, and they work great. They fire faster. They're a little more expensive, so it's a trade-off. And ultimately, this whole lightning protection game is a trade-off. You look at, so if I'm in, say, Washington State, where they get relatively little lightning, I'm probably not going to invest nearly as much as if I'm in Alabama or Florida or down in the Southeast. If I've got a $5,000 translator transmitter at a site, I'm probably not going to drop $500,000 on grounding and surge protection. Whereas if I've got a 80 kilowatt FM plus HD system that run on the wrong side of $250,000, or a TV site where it could be well over $500,000, then I'm going to invest a little more on protecting that investment. So again, there's an ROI formula that needs to be done almost every time. But at the very least, single point grounding, surge protector, and throw some ferrites on there as an added bonus. Now, the surge protector is the path between the AC wiring and ground. You remember I said earlier, ground's got a resistance. So if you run a lot of current down the tower from a lightning hit, it hits that earth with that resistance, and there's going to be basically a voltage created. So you're going to have potential there. Well, after that potential gets above the potential of the AC lines, which typically are going to be 240, 480, 600 volt, then the AC lines, with all their millions of miles of wire and inductor transformers and ground leads, become a much more attractive path to dissipate. So at that point, all this energy at the base of the tower, and here's something to think about. I would hazard a guess that the vast majority of switching power supply failures, whether it's wall warts on a processor or remote control, whether it's switching supplies inside a transmitter, the vast majority of those failures are probably from tower strikes, not from AC line strikes. But you still can't get the AC power line, especially if you're on the end of a line in rural areas, which most transmitter sites are. So surge protector, an MOV is bidirectional. It doesn't care which way the energy is growing. Ground to the AC lines, AC to ground, irrelevant to it. It will absorb a certain amount of energy before it fails. When it fails, it'll always fail short, so it needs to be fused. Anybody who's ever seen an MOV on a transformer where you got two legs and a little puff of white dust in the middle has seen the impact of what happens when an MOV is unfused. By the same token, you don't take the fuses because they failed out of this particular box on the wall in this picture and replace them with 7/16" bolts. Okay, I don't know what current of a 7/16" bolt is, but I can promise you it's a whole lot more than the 40 amps that the original paper cartridge fuse would blow at. So don't do that. All right, because MOV will 100% of the time fail short. If it's not fused, it will then fail open very, very catastrophically. And usually with a lot of loud noise and some smoke and a few cuss words from anybody in the vicinity. So the MOV goes between your AC line and ground. And if you do happen to get a power line strike, if the voltage goes above the clamp level of the MOV, it clamps and shunts that voltage ground. Life is grand. The equipment never sees it. By the same token, if you get a tower strike and ground potential spikes high and you've got a low impedance connection between that tower and that surge protector, again, it doesn't care which direction the surge is going. If you've got a 240 volt entrance with a 250 volt MOV and the ground potential goes above 490 volts, which should be the two together, then it's going to clamp the MOV and shunt the current out to the AC lines. So, and that's our ultimate goal here, is to, again, have the energy go around the equipment, not through it. So that's what we're trying to accomplish. There are tons of different MOV or surge protectors out there, or whether they're, again, MOVs or, again, silicon avalanche diodes is less a concern. But LEA, polyphasor, transtector, control concepts. We use a company called Raycap, which we've really liked working with. You get cheaper disposable ones. We use another one of those from a company called Merson. LEA makes cheaper ones as well. So, you know, there are a bunch of different options out there. The only thing critical is that you have one installed and put it as close to the panel as you possibly can. Okay. The challenge, and I'm going to skip past this one, but again, talking about short straight runs, the challenge is that the average transmitter site is built pretty much exactly wrong. AC comes in one end from the street, tower is at the back end in the field, and we hang all of the gear that we don't want to blow up in between. So what we're trying to accomplish is to take this, where all the energy has got to go through our equipment, blowing up supplies and amplifiers on the way, and get to something that looks like this. And that is the ultimate goal, is now the surge protector becomes the path between ground and the AC lines. Ferrite, just like I said, ferrite on their own, not going to do a whole lot if you don't have the short straight grounds and the surge protector. But if you've got a site where you've got the grounding done perfectly, the surge protector's in right, everything has been proofed and verified to be as good as it gets, and you're still seeing some failures, ferrites might make that little bit of difference that just tip you over the edge. So definitely something to pay attention to. All right. How do you fix an existing site? Well, there's a couple of things you can do. You put in the surge protector, establish a reference ground point. Maybe rerouting the coax so that instead of going out the back and then running a big long strap from a bulkhead at the right-hand side of this picture, you put the bulkhead over to the left and then reroute the coax. That'll do two things. You've increased the length of the coax, which increases its resistance, and you've improved the overall connection, decreased the distance to the ground point. So again, there are various things you can do to fix an existing site. If you've got a site that has evolved over a whole bunch of years with a whole bunch of rooms and a whole bunch of grounds going who knows where, sometimes it is easier to rip it all out and start over again. But in a lot of cases, you can just go through, like this one in Missouri. I think our total cost was 2 ground rods plus a $150 hammer drill attachment to drive ground rods into hard Missouri clay. So ballpark $250 there, plus a day of time, my time, and half a day of their engineer's time. And we reused the existing copper. And so there was no additional cost in that regard. So just something to think about there. Don't know who's calling me in the hotel room. Nobody even knows I'm in here, but there you go. The other thing we run into a lot, especially this time of year, is the is like Larry was saying earlier, it's been a hot year. So we do talk a lot about air handling. And there's two things that we really need to consider with air handling, and more so with forced air, but even with air conditioning, I've seen this get ignored a lot. We need to look at airflow direction. If you are air conditioning a room and you're not forcing the cool air through the equipment, well, you made the people really comfortable, but you're still burning up your gear. With forced air, that's even more critical. The air needs to go through the equipment that's being cooled. So we'll hit that in the next couple of slides, but definitely do that. Intake air has to be filtered. We really like positive pressure. So if you bring filtered air in with an intake fan and then exhaust it with an exhaust fan at a lesser amount. So say I've got a transmitter that's got let's say 1,000 cubic feet per minute of air throughput. So 1,000 CFM of throughput. If I bring 2,000 CFM into the building and dump it so the air intake is dumped directly into the transmitter air intake, and then use my exhaust fan to pull 1,000 CFM out, then I've got 1,000 CFM positive pressure. That means that filtered air is leaking out of every crack and crevice in the building. And you'll see it because of the way the door opens. If your door swings out and you turn the doorknob and it blows open in your face, you got good positive pressure. If you have to pull to get the door open, and what we run into a lot of, building will have air filter intake, no intake fan. They'll have a big old exhaust fan dragging the air out of the building, and it's also sucking dust in every crack and crevice and nook and cranny. So that's the reason for positive pressure. It keeps the room a lot more dust free. And especially with tube rigs, but even with solid state ones, the less dust you get in it, the less chance you're going to see arcs happen. And typically when an arc happens in a piece of RF gear, that's considered to be a bad thing. Okay. By the same token, I've run into a lot of sites where they're using air conditioning and they'll get a hot day in July and the air conditioning can't keep up, and they'll call and say, hey, you said we only needed a 5-ton air conditioner for this 60 kilowatt transmitter. And it's like, yeah, for the transmitter, but you've got to allow for convection heat on the building. So get an air conditioner tech involved. Don't just, unless you've got the training, don't do the math yourself. It's not something I would be good at. And, there are others who are better at it than me. So again, airflow direction. If you were looking from the ceiling, doing a bird's eye view, and you've got an intake fan on one side blowing air past the back of the transmitter at 100 miles an hour, you're creating a negative pressure zone and not cooling the equipment. You need to force the air through the equipment you want to cool. Okay, and this is critical with some transmitters more than others. So two things to remember. Some transmitters, the airflow path through it will take a lot of twists and turns, so there's a lot of inherent back pressure to the design, which means you absolutely need to force the air through the transmitter. So you've got to shove the air in and then draw the heated air out, okay, to minimize the back pressure. That'll do two things. It'll improve the cooling of the equipment. It'll also extend the lifespan of the fans in the equipment because they're not working with as much back pressure on them. Okay, the other thing is that you've got to pay attention to where the air intakes are located. Okay, so some transmitters, all the air comes in the back. I've seen some where it all comes in the front. Some, like our GV and NV Light series, the air comes in both front and back. In the front for the power supplies, it goes in, makes a U-turn, mixes with the air coming in the back to cool the modules and the combiners. So pay attention to what the manufacturer tells you and make sure that your airflow accommodates that. Okay, in a forced air system, this is even more critical, but it's also important in air conditioned. I've run into a lot of air conditioned sites where they dump a pile of cool air in the front of a transmitter where the air intake's in the rear. And again, it makes it really great for the operator, but the operator's not standing there 24/7, and that transmitter is. So make sure that we keep the transmitter cool. You know, we don't cool the building for the operator enjoyment. The other challenge is the folks that run, and I'm not going to say BART out loud, but I just did, and the subcaption changed it, so there, that worked out well. But or subtitle rather. Anyway, the ones that are designed for office and living space, the split units that send the cool air out top and have the warm air return down low. And for an office space, that works great because the cool air goes out at ceiling level and then cool air sinks so it settles down, cools everybody in the building, and nobody gets a breeze in their face. For a transmitter facility where the air intake is usually low and at the back or at the front, like I said before, or both, and the hot air, because hot air rises, is almost always, the outflow is almost always at the top, then what we need to do in those cases is get somebody with some sheet metal experience and flip the goes into and goes out of, so that we are pulling the heated air from ceiling level where it's going to be and sending the cool air down at ground level. And again, paying attention to the transmitter's specific air intake locations. You may need ducting to provide air front and back. You may need to move the ducting to put air around to the opposite side only. You know, again, it'll depend on your site, but what you absolutely do not want to do is cool the room and not cool the equipment. And I've walked into rooms that were almost meat locker cold with transmitters showing controller temperatures on the wrong side of 100 degrees. So definitely pay a lot of attention to that. Okay. And this would be a good example. So in this particular situation, the gray rack at the back of the picture toward the electrical panel is the transmitter. Air intake is to the left, exhaust is to ceiling level. The gray flex hose, that big gray 2-foot flex hose, is the cool air outflow, and the warm air return is the fan right below it, pulling the air away from the transmitter intake. So the transmitter was getting super hot, and it was seeing a lot of supply failures. Supplies will tend to go first. Switching supplies don't like to run hot. You'll, depending on the transmitter, if you run an HD gear, HD controllers, computers don't like to get hot. So there are various things. Controllers in general don't like to get hot. So pay attention to the airflow and make sure. Now, in this case, what we did, we put an exhaust duct on above the roof of the transmitter, connected it to the outflow, and then redirected that fan to just dump it the cool air intake to dump it right down on the ground right behind the transmitter. And again, reusing what was pretty much already there. We didn't have to add a lot of cost to it, but we were able to fix it with what we had. So just something to think about. Other thing to pay attention to is you can overdo it with air conditioning. Make sure that your air conditioning is sized so that it runs often enough to remove the humidity from the room, because every transmitter out there is spec'd for 0 to 90 or 95% humidity, non-condensing. And that non-condensing part is kind of key here, because if you're not cycling, if you've got an extremely oversized air conditioner that's not cycling often enough to keep the humidity level down, then you're going to end up creating some condensation. And I'm here to tell you, electronics do not like water. Okay. So those are the key things, really. It's like I told somebody once, I said, cool, clean, and well grounded are the three things. I don't care what piece of electronic gear you're working with. If you follow those three philosophies for everything, it'll all live a whole lot longer and you get called a whole lot less. Um, I've had people ask me how often should I replace the air filters, and the answer is I don't know. It'll depend on your transmitter site. It is specific one from one to another. Up here in the upper Midwest in cottonwood season, I've got sites up here that they swap out the filters almost weekly for a couple of months in June, or a couple of, yeah, well, it feels like a couple of months, couple of weeks at least. Now, for the rest of the year, it might be every 3 or 4 months. So it does vary, and it does depend on your site. If you're in, I've got customers with sealed air conditioned buildings where the transmitter filters don't only get replaced every 2 or 3 years, if that. So one of the things you can pay attention to is if you've got a thermometer with remote readability, and there, I mean, so many of them out there now. Shoot, even like some of the Wi-Fi temperature meters for cooking barbecue, whatever. Get one of them, hang it at the intake. Get another one, hang it in the exhaust stack, and pay attention to the delta, the difference between intake air and exhaust air. I can tell you on most of our gears, these days, our design spec is 10 degrees Celsius or 18 Fahrenheit when you're running at full power between intake and exhaust. If you see that, everything's grand. If you're higher than that, everything is not so grand, and you need to address it. So, whatever gear you've got, whether it's us, whether it's Gates Air, whether it's Elenos, every manufacturer should be able to give you an idea of their typical heat rise. And if you know what the typical heat rise is, then you can measure intake air versus exhaust air and have a pretty good idea if you're within spec. I don't have it right at hand, but another thing I'm a big fan of, less for that, but it's useful for that, is the little thermal cameras like the FLIRs. And I like the FLIR because I can plug it into my iPhone and just turns the iPhone camera into a an infrared camera. So it's, unless you're a certified, what do they call it, a thermal, there's a training, an actual title for somebody trained in using thermography gear, thermographer probably, but you're not necessarily going to get an exact reading. But if you use the same philosophy or the same method to take the shot every time, you at least should have an indication whether something's hotter now than it used to be. Um, and again, there are lots of courses that you can take to teach you how to use these things. So it's really useful skill to learn. Okay, especially another example would be circuit breaker panels. Um, Talked about the walkthroughs too, and I see Larry unmuting. I think he has an idea.
Oh, no, I was just going to say, yeah, we did that once before, and we put a meat thermometer in the
Uh-huh.
outtake so we could read it. And
Yep.
we knew that we were running okay as long as it stayed on lamb chops.
Right,
That was our
exactly.
key, was it sitting on lamb chops we knew we were okay.
Well, and these days with the little, I mean, you get the little PTZ cameras for next to nothing. I mean, you can get a Wise PTZ camera for 60, $70. So even if you've got a regular old dial-up meat thermometer stuck into an exhaust vent, you can have a PTZ camera aimed at it and read it over the internet. So yeah, no, that's a. I don't know about lamb chops necessarily, but that that's going to stick with me for a while now. And yeah, so let me see. I think my battery might be dead on this, but let's find out. Unlock iPhone. Oh, maybe we'll have some valid. Maybe it will work. So now I've got to find and again, so I've got the iPhone attachment on, and it is connected. So I should be able to, if I can remember how to work this thing. I'm just going to hold it up to the camera in a second, but FLIR. Yeah, so it's not the right one. That's search. Larry, I'm going to need somebody to teach me how to operate an iPhone. I need
Good
a
luck.
grown up. Yeah, there we go. Settings, allowed. Okay. Search. Clear one in apps. There it is. Okay. Yeah, done. And there. Okay, so I mean, that's exactly what it does. It takes a thermal image. There we go. So there's me.
Ooh,
And it's, like I say, it's reasonably good. There, I can't make this thing do it the way I do with my Samsung, but yeah, when I say a little bit of training, they're a handy tool to have. Yeah, did I turn it off and on again? So Scott says he's going to change all his temperature alarms to lamb chops. And what I'd say is that you want to, I'd set the temperature alarm for medium rare, rare, and well done or whatever. And that'd be my cue. It's like, uh-oh, yep, transmitter's well done, too late. But so this picture here comes back to the walkthrough requirement too. This is the bowl insulator on the ATU for a 50 kilowatt AM, and ants had built a nest in it. And every time it got humid, which in Arkansas it did a lot, it would start arcing, which really reduced the ant population, but it didn't do anything to keep the transmitter on the air. So, so that's, I guess, my nutshell. Like I said, keep it cool, keep it clean, keep it well grounded. And let's be careful out there because holy smokes, there's nowhere near as many engineers as there were when I started doing this 34 years ago. And I'd like to not see any attrition due to other events. By the way, if anybody's interested in ferrites, I threw this in here for the recording. I'll leave it up there long enough for you to grab a screenshot. But several articles about ferrites and permeability and stuff along those lines. So certainly any questions, you can shoot them to Larry if you don't know how to find me, or you can shoot them to me direct. And that, in a
yeah.
nutshell, was,
I have one
yeah.
question to ask. I had somebody ask me that
Hmm.
if you put a ground rod at the tower and
Uh-huh.
you ground rod at the transmitter building, do
Uh-huh.
those two ground rod systems need to be tied together?
Oh, absolutely. Yeah,
Okay.
because like I said, the resistance, relying on earth resistance, number one, it varies a lot from one location to another. Number two, it varies a lot between a rainy day and a dry day. Give you an example. I had a site in Tennessee where they did not have, basically they didn't have any ground rods driven at all to stabilize the resistance of the field. And between a dry day and a wet day, the common point impedance changed from 60 ohms to 40 ohms.
Ooh.
So it made the transmitter very, very unhappy. Well, the transmitters typically don't care a whole pile about a resistive change, but there was some inductance involved, and it threw the power readings off. So yeah, no, having them tied together is crucial. And there are situations, you and I talked about one once, where the building and the tower were almost right adjacent, in which case one ground rod would probably do the job for both. But yeah, like I said, it is situational. But as a rule, if I've got two ground rods, I want them bonded together.
Well, Jeff, we really appreciate all the information that you shared, and I'm sure if anybody has any questions, they can get a hold of you,
Yep.
either through me or directly to you. Oh, I got the wrong slide up, but that's okay. It's sort of like yours and everything. But we appreciate you being with us today. It was most informative. Want to remind everybody that our next webinar will be on Tuesday, July 16th, same time. And also, Jeff will be back with us in August. August the 8th and 9th is the annual ABA convention in Birmingham. We have a seminar, engineering seminar scheduled on the 8th. You can go to the website, ABA website, and check all that out. We have 4 really great presentations. Kirk Harnett will be there talking about the status of audio over IP and cloud production. A gentleman by the name of John Malik, who is with Imagine Communications is going to talk about SMPTE 2110 for all you television guys. Then Sean Edwards with, well, what used to be Shively. It's a different name for the company now, but Sean's going to be talking about FM combiners, how they design, how they put together, because you see a lot of stations now where they're using a common antenna. And then Jeff Weldon will be there. And I put him last because he said he was not going to get there till about 2 a.m. that morning and he needed his sleep. So his topic's going to cover when you go to the transmitter site weekly, and I underline that weekly, you need to visit your transmitter site at least weekly. He's going to talk about what you need to look at. Then there's a lot of stuff that you need to look at. So
I won't tell you when the last time I went to my transmitter site was, but it's been more than weekly.
oh, things can happen within a week, you know that.
Yep.
So join us at that if you will. There's the address down at the bottom of the screen there, www.al-ba.com. There you can see all the information about the goings on. We'll have exhibit booths set up. You can talk to all the vendors and Ted Hand, the president of the SBE will be there, and he'll be talking about the benefits of SBE membership. So Jeff, thanks again for being with us, and thanks everybody for joining us, and we'll see you again in July.
Thanks, Larry. See y'all.
Thanks.